Hey everyone, welcome to IEC Indy's second year review for final exam video. I've created a PDF for you to be able to print off or download to use and fill out and take notes as we go through this video together to better prepare you for next week's final exam. If you haven't had a chance to be in class yet for our labs and don't have a printed out version of that, like I said, I've included in the CMS a downloadable copy of this PDF for you to be able to print off and fill out. Or if you want a printed out version, you don't have the ability to print out at home, I will gladly print one off for you and give it to you when you come into class for your lab today. So that being said, let's jump right into our review for the final exam. All right, so the topics of our exam. I've listed here a good amount of what the exam will cover. Things that you need to study to better prepare yourself for this exam. I put first and foremost motors and motor calculations because it's the heaviest subject in the exam. Motors and motor calculations take up maybe 1/3, maybe a quarter of the exam, whereas everything else fills in the rest. Next would be transformers, single phase, three phase, calculations, and we'll get into that as well. Then it comes AC theory and RLC circuits. You'll see some of that throughout the exam, as well as Ohm's law, both for single phase and three phase circuits. We will touch base on wiring methods, including raceways, conduit fill, box fill, the use of cable, stuff like that, as well as grounding. For grounding, we'll get into all the terminology and code references for grounding and grounding electrode systems. Services, we'll touch a little bit on services as well as conductor ampacity, derating the ampacity of conductors, whether it be in a high temperature area or in a raceway with more than 3 current carrying conductors. And then also I put on here as well the NEC, because there's going to be an assorted amount of different code questions involving different areas of the code, and we'll get into that here together. Let's start, however, first and foremost with motors. Motors and motor calculations. Now, I've given you throughout the last few weeks of lessons a roadmap to motor circuits. We'll go over that here together, but I want you to know that you can use that roadmap to motor circuits on your exam. Again, knowing the steps for calculating motor circuits. What's the table FLA? Well, that's found in 430.247 through 250, depending on if it's a DC, single phase, or three phase motor. Remember, table FLA stands for tables, the table's fixed amperage for a full load amperage for that motor. Not necessarily what's going to be found on the nameplate, but it's the table FLA, the table full load amperage for those specific motors. Branch circuits, 430.22, short circuit and ground fault protection, 430.52, heaters or overload protection, 430.32, feeder conductors supplying multiple motors, 430.24, and overcurrent protection devices for feeders supplying multiple motors, 430.62a. Let's look at the roadmap for motors together and walk through each step just so you have a quick review of motor calculation. Let's look at the roadmap to motors together. We start with our motor FLA, or the table FLA, found in code article 430.6 and in tables 430.247 through 250, depending on the style of motor, whether it's DC, single phase AC, or three phase AC, or polyphase as they like to put it in the code book. These are our table full load amperages. Our full load amperage is our running current for these motors, not necessarily the current that it takes to start them up, but our current running at its rated horsepower and its rated RPMs. Next, we have our branch circuit conductor sizing and our branch circuit overcurrent protection device, or better known as our short circuit and ground fault protection. But first, let's look at branch circuit conductor sizing. This is found in article 430.6 indicating for us to look at 430.22. And in 430.22, we find that we have to increase the circuit conductor's ampacity to 125% of the table FLA for that individual motor. Now, this is for just one motor, not a feeder supplying multiple motors, just one motor. So this would be a branch circuit conductor. We increase the conductor's ampacity from the table FLA to 125% of the table FLA. And then our branch circuit overcurrent protection device, or like I said, better yet, the short circuit and ground fault protection for our branch circuit is going to be found in Article 430.6, directing us to Article and Table 430.52. Now, 430.52 asks us to increase the size of our branch circuit, short circuit and ground fault protection to allow the motor's inrush of current or its locked rotor amperage to take place and actually get the motor started. However, this does not protect the motor against overloads. It only protects the motor against short circuits and ground faults, that rapid increase in amperage, as opposed to an overload, which is a gradual increase in amperage. To protect a motor against overload, we use something called heaters. We'll get into that here in a second. For branch circuit, ground fault, and short circuit protection, you'll use the table 430.52 and apply that percentage to the table FLA found in table 430.247 through 250 for the specific motor. Typically, for dual element time delay fuses for a standard single phase or a standard three-phase motor, you're going to increase the ampacity by 175%. And for an inverse time circuit breaker, it's going to be roughly about 250%. But again, reference the table when coming across these questions to make sure you have the right information in front of you. Let's also look at motor circuit overload protection. Motor circuit overload protection, or heaters, are found in 430.32 and table 430.32. 430.32 indicates the sizing of these heaters. Now, the beautiful thing is, in the industry now, manufacturers have taken all these calculations into effect or into account when they size and publish their heaters for specific motor starters. So being able to identify how many heaters am I putting in the starter, and what is its ampacity rating, and then what is its ID number is important. For the exam, you will not need the annex from the back of your manual. If there are any heater questions or any kind of overload questions, the table will be provided for you in the exam. You are not to use your manual during this exam. Now let's look at sizing feeder conductors with motor loads and overcurrent protection devices for feeders that have motor loads. Sizing feeder conductors with motor loads is found in 430.24, and overcurrent protection is found in 430.62a. For sizing our feeder conductors with motor loads, I will take the largest motor and increase it by 125%, and then add the remaining table FLA for any other motors on that feeder. So for example, let's say our two motors here, one has a table FLA of 10 amps and one has a table FLA of 27 amps. Which one of these two is the largest motor? And both of these motors are both run, I don't know, by the same voltage, 208 or 230, doesn't matter. They're the same voltage, but one is greater than the other in horsepower, so it equals to a larger amperage. I will now take my largest motor's table FLA of 27 and increase that by 125%, or 1.25. So that 27 times 1.25 equals 33.75 amps. So that's just for that one motor. Now, I add to that 33.75 amps my remaining table FLAs. The only other motor I have left on this feeder is a 10 amp motor. So I add 10 amps to 33.75, giving me a total of 43.75 amps. So with my now newly calculated ampacity of 43.75 amps, I go to table 310.16 and determine my wire size. And this is going to be based off of the terminations, which is typically going to be found in the 75-degree column. So I would probably install a number 8 wire for this application at minimum. Now that doesn't include any non-motor loads running at either continuous duty or non-continuous duty. If there were any other non-motor loads, I'd add those to the feeder as well. So that being said, let's look at sizing the overcurrent protection device protecting that feeder. So the overcurrent protection device protecting that feeder would be based off of the largest overcurrent protection device on the individual branch circuits of the same style. So let's say we want to install a circuit breaker right here. That means all of my math for calculating the size of that circuit breaker would be based on if these were circuit breakers as well. That doesn't mean they have to be circuit breakers. That just means that my math has to be based on as if they were circuit breakers. So let's figure out what each individual branch circuit's circuit breaker would be according to 430.52. So 430.52. I'm going to increase for a circuit breaker on a generic 3-phase motor. For a circuit breaker would be 250% for each of these. So let's do the math. 27 amps times 2.5 gives me a total of 67.5 amps. 67.5 amps. Now, because this is a branch circuit and I have exceptions that allow that to be raised up to the next standard size circuit breaker, I look in Article 240.6 and I increase that to 70 amps. My handwriting's awesome. There we go. 70 amps. That's for this branch circuit right here. Now, let's look at our next branch circuit, which is 10 amps. 10 amps times 2.5 equals 25 amps. 25 amps, I believe, is a standard size circuit breaker. So I can put that here as well. Now, which one's the largest? I only need to use the largest in my calculations. So my largest between 70 and 25 would obviously be 70. So I'm going to use 70 amps as my starting point. I take 70 amps according to 430.62 and I increase that by the table FLA of the remaining motors on the circuit. That would be this guy right here, 10 amps. So 70 plus 10, 80 amps. That means I have an 80 amp breaker to install on the feeder, protecting this 70 and that 25. That being said, let's say our math didn't come up exactly to 80 amps. What if it came up to 83? Well, I don't have permission, according to 430.62a, to increase that to the next size up. I only have permission to go back down to the next standard size. There's no permissions on a feeder to go to the next size up. On a branch circuit, you can go to the next size up. For an individual motor, if there's just one motor, branch circuit, you can go up. If it's a feeder controlling multiple motors, I only have permission to go down to the next standard size. So in this situation, 80 amps is a standard size. I'll stick with 80 amps protecting that feeder. You can review this again if you need be. Until then, let's keep moving on. Code references for motors. 430.1 is the one-line diagram for navigating the NEC Article 430. I highly recommend getting familiar with that. It'll help you navigate Article 430 when it comes to motor code. 430.6, reference to the FLA of motors found in the tables. We talked about that earlier. And then our table FLA for DC motors, table FLA for single-phase motors, and table FLA for three-phase motors is found in Article 430.247, 248, and 250. Nameplate versus table FLA of motors. The table FLA is used for most motor calculations. This includes, but not limited to, branch circuits, short circuit, and ground fault protective devices and feeders. When you're calculating branch circuits, short circuit, and ground fault protective devices, feeders, all of those, you're using the table FLA and not the nameplate FLA. When you need to use the nameplate FLA is typically used, but not limited to, voltage drop calculations and the sizing of overload protective devices or heaters. That's typically the only areas you're going to use nameplate FLA for. Voltage drop corrections and the sizing of overload protective heaters in these scenarios. Single-phase transformers. Let's get into transformers now. Single-phase transformers. Turn ratios between primary and secondary windings. Understand dual voltage primaries and secondaries and Ohm's law. You're going to see on the exam different questions relating to the turn ratios between a primary and secondary winding. Now, if I have a primary winding of 480, it's really good handwriting there, 480. I need to get my stylus back. I have no idea where it went. Let's try that again. 480. And that's my primary. My secondary would be 240. What would my turn ratio be? I simply divide the two together. 2 to 1. My turn ratio for my voltage would be 2 to 1. And inversely, my turn ratio for my amperage would then be 1 to 2. The amperage on the primary would be 1 to twice the amperage on the secondary. That's turn ratios. Dual voltage primaries and secondaries. For a dual voltage primary or a dual voltage secondary, that means there's two sets of windings in each transformer. Each of those windings is rated to the lesser of the 2 volts. Let's say we have a 120, 240 dual voltage primary. Each of these windings is only rated up to 120 so that they can be connected in series in order to make them receive the 240. Or they could be connected in parallel to receive the 120. And now Ohm's law for single-phase transformers is the same as typical Ohm's law that we've seen so far. Where Ohm's law in transformers begins to get tricky is when we get into three-phase voltage. Three-phase transformers. Turn ratios between primary and secondary windings. Pretty much the same, except you have to consider that for all three phases. Understand the dual voltage primaries and secondaries pretty much the same, except that it applies to all three phases. So if I've got a dual voltage primary, that means each primary phase has 2 windings. And if I have a dual voltage secondary, that means each leg or each phase in the secondary has 2 windings. And again, remember, each winding is rated for the lesser of the 2 voltages, i.e. 240 and 480, like we talked about a slide ago. Now with Ohm's law and 3-phase, remember to include the square root of 3 in your calculations, because a 3-phase voltage is not in sync with itself. It's not in phase with itself. It's off by 120 degrees. Therefore, you can't just add up the voltage. You have to include the square root of 3. And then the rules of delta connected transformers and the rules of Y connected transformers. Let's look at all this together. For a delta connected transformer, the coil voltage versus line voltage in delta transformers. Coil voltage is the same as line-to-line voltage in delta transformers, meaning if I've got line-to-line voltage, it's going to equal the same as end of coil to end of coil voltage in a delta transformer. So if I've got a delta transformer, let me draw this out here. Here's my delta, and I've got 3 lines coming off that delta. The voltage between these 2 lines is the same voltage that you would find at this point and this point, between these 2 points. So if I receive 240 volts here on my meter, I'm going to have 240 volts between the 2 points of that triangle. So voltage is the same or constant in a delta transformer, whereas current is off by the square root of 3, meaning using these formulas here, the amperage of a delta is 1.732, or the square root of 3 times the coil's amperage, and vice versa. The coil's amperage is the line amperage divided by the square root of 3. I would write these formulas down and use them in your notes. And this is for delta only. You'll see here in this diagram, a little bit better than my drawings, that's for sure. You'll note that the voltage at line 1 and line 2, right here, line 1 and line 2, is 240 volts. Now if I took my meter and put it between any given point, line 1, and this I guess is line 3, you'll note that the coil voltage is the same at 240 volts, just as if it was between L1 and L3 over here, 240 volts. However, the current, our line current, 180.4 amps, is actually, if you were to take 180.4 amps and divide it by the square root of 3, you would find that you actually have 104.2 amps on each winding. I have 180.4 amps on my lines and only 104.2 amps on my windings. That's what I mean by the amperage is off by the square root of 3. The formulas for a 3-phase power, I would write these formulas down. Make sure you have them in your notes. Remember, you're including the square root of 3 every time you're doing a calculation regarding Ohm's law and 3-phase power. Now let's look at Y-connected transformers. A Y connection requires that the single-phase transformers be interconnected so that X's, 1's, or X2's of all 3 transformers are connected together, giving it a center point being right here. In this scenario here, they used X2, and that's where they came off and grounded it, allowing them to have a neutral conductor. And you'll note that each of the lines or phases is leaving the other end of the winding, going to A, B, and C. Another way of looking at this is an example here of a delta connected primary This here is delta connected, and a Y connected secondary. This here's Y connected. You'll note that X2 of each transformer on the secondary is connected along the same line as the neutral, meaning that X2 is our center point. And X1 goes all the way to A phase. X1 of transformer 2 goes all the way to B phase, and X1 of transformer 3 goes all the way to C phase. There's nothing else that the phases are connected to, meaning that's a Y connected scenario. Whereas in our delta connected primary, transformer 1's H1 is in tandem or parallel with or connected with H2 of transformer 3. So I have two windings connected together at the same point. Same as with H1 of 3 and H2 of 2. They're connected at the same point along C phase. And H1 of 2 along with H2 of 1, they're connected together at the B phase. This would be an example of a delta connected primary. Now for the rules of Y systems, very similar to our rules of delta systems. Coil voltage is off from the line-to-line voltage by the square root of 3, meaning you're going to use these formulas here when determining line or coil voltage. This one here is for line-to-line voltage when you know your coil voltage. The E of line equals the E of coil times the square root of 3. So let's say we had a coil voltage of 120 volts. Multiply that by the square root of 3, you end up with 208 volts, roughly, which is why a lot of our systems is a 120-208 transformer. Those are Y-connected systems. And inversely, if I were to take that 208 and divide it by the square root of 3, it would give me 120 volts for my line to ground or my line to center point. A better way of looking at it is right here. You'll note that between A phase and B phase, I'm reading 208 volts on my meter. Yet between A phase and the center point, and let's say that that's ground, I'm only reading 120 volts here. That is, if I were to take 208 volts divided by the square root of 3, it would give me that 120 volts. So that's the rule of a Y voltage, a Y connected transformer and regarding its voltage. Line to line is greater than line to ground by the square root of 3. So for me to figure out if I know my line to ground, I just multiply that by the square root of 3. That will tell me what my line to line would be. Again, with rules of Y systems, coil amperage is the same as line amperage. Coil amperage is the same as line amperage, meaning it's constant. If I have 10 amps in my line, I have 10 amps in my coil, period. Coil amperage is the same as line amperage of a Y system. Again, the formulas for you to make sure you have written down: I line of Y equals I coil of Y, and E line of Y equals equals the square root of 3 divided by E coil of Y, and then inversely with the other way around. Just make sure you have these formulas written down. And this picture, just like the earlier one, illustrates the same. You'll see that I have 208 volts across each winding. Each line here, 208 volts. And if I were to take my meter between at one end of the winding and the center point, I only have 120 volts. Whereas the ampacity of my line, let's say I have 208 amps on line C. On winding C, I still have 208 amps. It's constant. So just knowing what's constant and what's off by the square root of 3 will help you in your calculations. Also for transformers, NEC Article 450, for transformers, anything regarding transformers, the sizing of a transformer vault, the sizing of a fire, what's the fire rating of a transformer vault? All of these are found in Article 450 when you're doing your keyword searches. AC theory and RLC circuits. You will see some questions regarding AC theory and RLC circuits on your final. AC power generation, frequency and sine waves, the definitions of RLC components, inductance, capacitance, etc., and then RLC formulas. Make sure to use the sheet you were given. If you look back on the CMS, I believe I have given you a handout regarding RLC formulas and equations. Make sure that you hunt that down. That is allowed to be used on the exam. I have no problem with that. But please look those up. Some of the definitions of inductance. What's an inductance measured in? What's capacitance measured in? I believe inductance is measured in henries. And capacitance is measured in farads. That's a D, not a P. There we go. Farads. So those things are things you need to keep in mind. RLC formulas that I know you need to keep in mind would be, what's your formula for inductive reactance? Again, these formulas you will need to be aware of and how to use them. Other formulas you may need to use found here for impedance. Impedance again is the total opposition to current flow in a circuit. And these two here are for series circuits. So Z equals the square root of R squared plus XL minus XC squared. XL would be your inductive reactance, XC would be your capacitive reactance. Know how to use those formulas. Go back and study from lesson 212 through 214 how to use those formulas. In a parallel circuit, the total impedance is the same as the applied voltage divided by the total amperage. And to figure out your total amperage, it would be the square root of IR squared plus IL minus IC squared. Very similar to our Z of our impedance of a series circuit formula. So write those formulas down. Make sure you have those with you next week for the exam. Again, the whole purpose of this is to determine the overall electricity used or power used in an overall circuit. Again, watts would be the real power. That's what does the work. The VARs, or the reactive power, that's wasted energy just to overcome resistance or to overcome opposition. Put those together, you have your overall power of the circuit being used. So just to keep in mind, that's what the whole purpose is of understanding inductive reactance, capacitive reactance, real power, reactive power, and apparent power. The whole thing together would be apparent power. This guy right here. That's apparent power. Again, with Ohm's law, review your Ohm's law formulas, series versus parallel circuits, three-phase Ohm's law problems. You will see all of these on the exam. So reviewing Ohm's law formulas, again, write these formulas down. I equals E divided by R, E equals I times R equals E divided by I. You remember, some of you may use the triangle method. Some of you may use the Ohm's law wheel method. Either is great. Just make sure you understand and know your Ohm's law formulas. More formulas for you to keep in mind is formulas for power. You can make sure you have these formulas written down so you know what your go-tos are for Ohm's law. P equals I squared times R. P equals E squared divided by R. P equals E times R, which we already, we've talked about earlier today. And then R equals E divided by I, or resistance equals volts divided by amps. E squared divided by P, and then P divided by I squared equals R as well. Again, if you have access to an Ohm's law wheel, you're more than welcome to use that. Series versus parallel circuits. You will see questions like this. So what would the voltage be at every load when a parallel circuit suddenly becomes a series circuit, aka you lost the neutral? Because before it was a parallel circuit, now it's a series circuit. So let's look at an example together. Yep, the ever famous toaster and garbage disposal question. If I have a toaster and a garbage disposal and they're connected to the same outlet, and that outlet is a split outlet, one side's ran from one leg, one side's ran from the other, equaling 240 at that outlet, but they share the same neutral going back to the neutral bar, what would the voltage be at the garbage disposal if the neutral were lost? Well, let's look at this together. First and foremost, what do we need to determine? We need to determine the fixed resistance of every load involved. So let's go ahead and calculate using their overall ratings and their rated voltages before we apply any other voltage to them. After we've calculated using all those Ohm's law formulas, we can determine that their fixed resistance would be per equipment listed here below. Our toaster is 14.2353 ohms. Our garbage disposal is 11.2069 ohms. And our water heater is 11.5739 ohms. Now, in this question that I just asked, the water heater is not even involved. So we can just eliminate that from our equation. The water heater is not even involved at all. So in reality, what we need to keep in mind is the toaster's voltage, the garbage disposal's voltage, their resistance, and their amperage as we determine how this works. Now, all of this, these ohms, these were based on the rated voltage, not anything applied, the rated voltage. So, with that given, that's its true fixed resistance. Let's apply some math and determine just how many volts we'd see at that garbage disposal if we lost a neutral. So, we start with our total. We need to figure out what our overall resistance total is between our toaster and between our garbage disposal. In order to do that, we take the resistance of each one and add them together to get our R total. Our R total in this case would be 25.4422 ohms. That's for these two alone. Once I've determined the overall resistance between the two loads in question, I then need to compare it to its applied voltage or its total voltage in order to get the total amperage that I would have between the two devices or two appliances. In order to do that, I need to take the E total, which is 240 volts, and multiply that times the R total, which we already determined is 25.4422 ohms. Multiply those two together, 240 times 25.4422, and you'll end up with 9.4331 amps. So now we know our total resistance for the circuit. We know our total amperage for the circuit, yet we want to determine just how many volts are now being dropped across the garbage disposal. And remember, voltage in series is additive. So these two, based on their resistance, are going to divide that 240 volts proportionately between the two. It's not going to be 120 this one, 120 that one. It's going to be a division, not really division, but it's going to be divided amongst the two based on what the resistance is. So in order for me to determine what my garbage disposal is going to be, I take my I total and I multiply it by the resistance of the garbage disposal. Remember, E equals I times R. going back to Ohm's law formulas. E volts of the garbage disposal equals the I, the amperage of the overall circuit, times the resistance of just the garbage disposal. When I calculate that all together, I end up with 105.72 volts just at the garbage disposal alone, leaving the rest to be used up at the toaster. So that's an example. You will see questions like that on the exam as well. And again, with three-phase Ohm's law, I can't stress this enough because so many people miss it. Remember to include the square root of 3 when calculating three-phase Ohm's law questions. Three-phase power, for an example, is P equals I times E, or in this case, it's P equals I times E times the square root of 3 to get a true calculation for three-phase power, because we can't just add the voltage together. It's off by the square root of 3, so it's got to be calculated according to the square root of 3. Wiring methods. Raceway systems, conduit fill, box fill, pull box sizing, underground wiring. You're going to see questions regarding all of these on the exam. Let's look at raceway systems first. A raceway is an enclosed channel designed expressly for holding wires, cables, or bus bars with additional functions as permitted in this code. This is the definition right out of Article 100 in the NEC for a raceway system, or for a raceway. Some common examples of raceways: IMC, RMC, FMC, PVC, EMT, and these numbers that I've placed next to their names or their abbreviations are the code articles regarding these raceway systems. So if I have questions about securing and supporting IMC, I'm going to look in Article 342. If I have questions about EMT and uses permitted versus uses not permitted, I'm going to look in Article 358. And I'm going to look at their specific dots for those locations or those examples. And I'll get to that here in a second. For a cable assembly is not a raceway. It's a flexible assembly containing multiple conductors with a protective outer sheath, which its purpose is to protect the conductors contained within. Now, the difference between MC cable and flexible metal conduit is that the cable assembly has been pre-manufactured with the conductors in them, whereas a flexible metal conduit, you're installing the conductors yourself and have the ability to remove one or more individual conductors at will. Whereas a cable assembly is typically braided together and you aren't able to remove just one conductor, typically. Common examples of cable assemblies: AC cable, MC cable, NM, NMC cable, Romex, SE cable, which would be service entrance cable. Again, these are numbers next to them are the articles that completely are dedicated to those cable assemblies. Now, I told you about the dots. So like with cable assemblies, 334 is Romex. I would turn to 334.2 for my definitions regarding this cable. I would turn to 334.6 for the listed requirements for this raceway or cable, for this cable. I would turn to 334.10 for uses permitted, 334.12 for uses not permitted, 334.26 and 24 for bends, number of bends permitted in one run, 334.30 for securing and supporting, to make sure I know what intervals to secure and support these things at. And then anything regarding boxes and fittings, I would turn to 334.40. I would write these dots down as they will be useful to you in the exam. Conduit fill, Chapter 9. Chapter 9, Tables 1, 4, and 5 is where we get our conduit fill. Chapter 9, Table 1 gives us a cross-reference, or not cross-reference, I'm sorry, a percentage of fill allowable. Table 4 gives us a cross-reference based on that percentage, and Table 5 gives us a cross-reference based on the type of conductor being installed. So Table 1, percent of cross-section of conduit and tubing for conductors and cables. One conductor means that I'm only allowed to fill that conduit up 53% if I just have one conductor running through there. If I have only two conductors running through there, I'm allowed to only fill it up to 31%. But if I have three or more, I have a 40% fill allowed for that raceway or that conduit. I would write these things down. Table 4 gives us your dimensions and percent area of conduit and tubing. The areas of conduit or tubing for the combinations of wires permitted in permitted in Table 1, Chapter 9. They give you in this table, let's say I have 3 or more conductors running through a raceway of EMT. It tells me just how much 40% of that raceway is, so I know what not to exceed when it comes to my number of conductors or my inches squared being consumed by conductors in that raceway. And then Table 5 gives me the dimensions of those insulated conductors, so I know just how many to add to that raceway. And again, this is review for you. You should at this point know how to size conduit fill based off of these tables. All right, so box fill. The number of conductors permitted to be in a box is found in 314.16. 314.16 spells out everything you need to know for sizing of small junction boxes, whether it's conductor fill, 314.16 B1, clamp fill, support fitting fill, device or equipment fill, equipment grounding conductor fill. All this is based on the cubic inches of the conductor inside the junction box. So again, a conductor fill, 314.16, each conductor that terminates inside the box will be counted as one conductor. Each conductor that passes through a box without a loop will be counted as one conductor. Each conductor that passes through a box with at least a 6-inch loop will be counted as 2 conductors. And now again, these are all current carrying conductors. This is not our equipment grounding conductor. These are our current carrying conductors, or our neutrals. So those would be counted as one or more than one conductor. Clamp fill, based on the largest current carrying conductor. Support fitting fill, based on the largest current carrying conductor. Device or equipment fill is based on the largest current carrying conductor connected to that device. So if I have a 10 gauge wire or 2 10 gauge wires connected to a receptacle inside that box, that receptacle itself would be counted as an additional 2 10 gauge wires. That's based 2 per device according to 314.16 B4. 2 per device for each yoke. So if it's a single gang device, it's counted as 2. If it's a double gang device, it's counted as 4, and so on and so forth. Equipment grounding conductor fill, 314.16 B5. It used to be you just count your grounds as 1 and that's it. But now in the 2020 code, it's only counting, my ground wires are only counted as 1 up to the first 4. So let's say I have a box with 7 7 equipment grounding conductors in there, and let's say they're 12 gauge, so 2.25 inches cubed per conductor. I'm not just going to take 7 times 2.25 inches cubed. The first 4 of those 7 I only count as 1 conductor, and everything after 4 I count as 1/4 conductor each. 1/4 conductor each, or 0.25. So I take my 3 times 0.25, 3, because 7 minus 4 is 3, times 0.25 equals 0.75. So I have a total of 1.75 equipment grounding conductors. Then I take that 1.75 and multiply it by its wire gauge size. So that's equipment grounding conductor fill. Once I've calculated just how many conductors and support fittings are going to be installed in that junction box, I need to see what its maximum volume is allowed to be. To do that, I use table 314.16b to get my wire size cubic volume, whether it be 14 gauge, 12 gauge, 10 gauge, 8 gauge, etc. I use table 314.16b to determine if I've got 10 gauge wire and I only have 3 of them, I take 3 times the volume of a 10 gauge wire, which would be 2.5 inches cubed. 3 times 2.5 inches cubed would be 310. No, it's more than that. I'm not using a calculator. 3 times 2.5, 7.5 is less than that. And then once I've determined I have 7.5 inches cubed used up in 10 gauge wire, I figure out what I have used up in 12 gauge wire. Then I figure out what I have used up in 14 gauge wire, if any. And then I figure out what I have used up in the devices and add those to that based on the wire size. Once I've determined my total cubic volume to be used up in a box, I need to make sure that I have the appropriate box for that particular installation. So then I go to table 314.16a to size the appropriate box based on the total cubic inches. This is based on total cubic inches. So I would use table 314.16 to size a junction box. Let's say I have a total install that uses 20 cubic inches of conductors and devices. I need to make sure that I have a junction box that can handle at least 20 cubic inches, which I believe a 4 square by 2.5 inch or 2 1/8, I can't remember which one it is, can handle up to 21 cubic inches, but I'd have to look that up in the table to be for sure. So that's why I would go to table 314.16a to find my appropriate box for that install. I've given you a table to help you figure out box fill calculations. You are permitted to use that table that I've given you. If you don't have that table, go back and look on the CMS. I believe it's lesson 208, somewhere around there, 208 or so, where you can download a PDF version of that box fill table and use it for your box fill questions. It's not really a table as much as it is a worksheet. Sizing of pull boxes. 314.28. You have 2 different types of pull boxes. These are for 4 gauge wire and larger, by the way. For straight pull, 8 times the largest conduit for straight pulls. And then for a right or a U-pull, 6 times the largest conduit plus the trade sizes of the remaining conduits on the same side of the box. And that's 314.28 A1 and A2. So for a straight pull, if I have a box, and let's say I have a 4-inch conduit here and a 4-inch conduit here, this box width between here and here needs to be 8 times that 4-inch conduit, 32 inches. The minimum width of that box would have to be 32 inches. And that's for just a straight pull. Let's say I have an angle pull or a right pull. In my box, I've got a 4-inch here, a 4-inch here, a 2-inch here, and we'll leave it at that. I would then take my largest conduit and I want to determine what's the width of this box. My width, not my height, my width. So I take my largest conduit, which was 4-inch, right? And this one was 2. I take my largest conduit, 4 inches, times 6, which gives me 24, right? Now I add the remaining inches to it. 24 plus 2, 26. The minimum width of this box needs to be 26 inches. For another example, all conductors enter the right side of the box and exit the box at the left side. What's my minimum calculated dimension for width? You see how they've drawn it for us. Well, what's our largest conduit? It looks like our largest conduit, going left to right, would be conduit H. Conduit H is 2.5 inches. 2.5 inches. And now I add the remaining conduits to that. Well, I take that 2.5 inches first off, 2.5 times 8. And that's it for a straight pole. I don't add here. 2.5 times 8 is what? 2.5 times 8 is 20. 2.5 times 8 is 20. So the width of this box would need to be 20 inches at minimum. So I guess in our answer it would be none of these here. Now for a right pole, or a right angle pole, not going straight through. For the pole box shown in figure 208.52, the minimum calculated width is blank inches. All conductors enter the bottom and exit the right side of the box. So we're calculating what? The width. We're looking for this guy right here. So that being said, I need to use this wall here to determine my width. What is the largest conduit on that wall of the box? Well, that would be my 4-inch. I take 4 inches, multiply it by 6 according to 314.28. That gives me 24. Then I add the remaining conduit sizes. 3 inches, 2 inches, 2 inches, 2.5, for a total of 33.5 inches. Is that one of our answers? You bet. So the answer to that one would have been letter C. That's how you do a right angle pole and a straight pole when it comes to large junction boxes or pole boxes that use all conductors 4 gauge and larger. Wiring methods, Article 300. Underground installations is going to be found in 300.5. Minimum burial depths of cables is going to be found in 300.5. Protection from damage, 300.5D. Buried splices, 300.5E. Backfill, 300.5F. Raceway seals, 300.5G. And the reason I bring these up is you will have a couple questions on the exam regarding underground installations. So knowing where to turn, underground installations, 300.5H for underground bushings, 300.5I for conductors, 300.5J for ground movement, 300.5K for directional boring. And again, I'm just trying to give you the basic code references so you can find what you're looking for when asked questions about it. Remember, for coverage, to turn to table 300.5 when it comes to amount of coverage over buried underground installations. Grounding, Article 250. We're going to look at terminology, grounding electrodes, purpose of grounding, and purpose of bonding. You'll see some questions regarding this on your exam. Terminology for grounding. Ground equals earth. That is what ground means. Grounded, connected to ground. A grounded conductor is a conductor that was intentionally grounded. I know this seems simple, but this is right out of the NEC Article 100. So knowing your terminology is going to be important for the exam. Equipment grounding conductor, a conductor that provides a low impedance path between equipment and enclosures and the system grounding conductor and the GEC. So understanding the terminology here, what's an equipment grounding conductor? What's its purpose is to provide a low impedance path between equipment and the system grounded conductor and the GEC. The grounding electrode is a conducting object through which a direct connection to earth is established. You will have grounding electrode questions on your exams. Grounding electrodes, I believe, are going to be found in Article 250.64 and 66. Grounding electrode conductors, I take it back, they're also found in 250.52, I believe, as well. So knowing your grounding electrodes, rod and pipe electrodes, knowing your ground rings, code articles referring to those, code articles referring to a concrete encased electrode, code articles referring to metal water pipe as an electrode. So 250.52, I believe, through 64 for grounding electrode systems. Here's an example of a panel. This guy right here, number 1, would be a grounding electrode conductor. You'll note that it's connected to the metal I-beam of the building. That metal I-beam is considered a grounding electrode. The green wire would be a GEC, or a grounding electrode conductor. Number 2 here, the white wire, would be a grounded conductor. It's intentionally grounded, and it's running with our ungrounded circuit. Number 3 would be known as an MBJ, or a main bonding jumper. Number 4 would be an EGC, or an equipment grounding conductor. And number 5 would be our ungrounded conductors, or our hot wires for our branch circuit. So know your definitions, know your terms, and what goes where in a panel. Grounding electrode systems, it was right, 250.50, 52, 53 for metal water piping, interior metal water piping, etc. Structural steel, 250.52. Concrete encased electrode, 250.52A3. Just going to give you the code references here so you know where to look answers up and you know where to find your information. Made electrodes found in 250.52. So we're looking at ground rings. A ground ring is supposed to be 20 feet of 2-gauge wire or greater bare copper, and it shall encircle the building, buried at least 2.5 feet down. Made electrodes continued. Rod and pipe electrodes. You're going to find that in 250.52A5. A minimum of 8 feet, minimum of 5/8 inches. If it's a pipe, minimum of 3/4 inch. And if it's a pipe, minimum of 8 feet. You'll find that right there in Article 250.52A5. Grounding electrode system. Construction and installation, other electrodes like plate electrodes, local metal underground systems, etc. found in 250.52 all the way through B1. The primary purpose of grounding metal equipment. This is found in 250.4 in the NEC, is to keep all metal parts at the same voltage and limit voltage surges. It has nothing to do with the operation or the quick operation of overcurrent protection devices. Does it aid in that? Yes. It's not its primary purpose. Grounding's primary purpose is to keep all metal parts the same voltage and limit voltage surges. Whereas bonding, the primary purpose of bonding is to cause the quick operation of overcurrent protection devices. We're bonding everything back to create a low impedance path back to ground, a low opposition path back to ground. It's a process of establishing continuity and conductivity through a connection. It's done to perform equipotential plane, meaning that if I have a fault at the very end of the longest branch circuit, that fault will travel across the metal enclosures all the way back to the panel and trip the breaker. Terminology for services. Terminology's definitions, you're going to find that in Article 100. Overhead and underground services. You will have questions regarding all of these on the exam. A service. What's a service? A service is conductors and equipment that provides electrical power to a building or structure. Service conductors. Conductors from a service point to the service disconnecting mean. So you'll have overhead and an underground, different types of service conductors. Different types of services all around. Service drop. Service drop is overhead owned by utility. Service lateral is underground owned by utility. Service point is where utility meets the customer service. So let's say utility has a pole with a transformer on it. You got a house here with a meter cabinet and a weatherhead. And the electrical utility installed the service entrance conductors, the service drop from the transformer to the weatherhead. This would be called the service drop. And this would be the service point. This is where utility meets customer. Everything from that weatherhead down would be installed by the electrician. Everything from past the weatherhead would be installed by the utility. That's if the utility determines that's where they want the service point to be. Remember, it's always up to the utility company to determine that, or the engineer, if he's worked it out with utility. Service equipment, all the equipment necessary to control supply of electrical power to a building. And here's an example here. I didn't realize I even had a picture with this. You'll see here we got a service drop. Point of attachment right here. Service point. That's where customer meets utility. Service entrance conductors, we were installing those through the meter to the equipment, the service equipment, the panel board. Everything from the weatherhead on would be installed by the electrician. Everything before the weatherhead would be installed by utility in this scenario. Utility makes the call, however. Overhead service conductors, locations. You're going to find that in Article 230. Minimum sizing. The smallest size copper for a service overhead is 8 gauge copper, 6 gauge aluminum, or 12 gauge copper for a single branch circuit service only, meaning that service only has one branch circuit. So 8 gauge copper if it's overhead, 6 gauge aluminum if it's overhead. Same with underground. If it's underground, 8 gauge copper, 6 gauge aluminum, 12 gauge if it's just a single branch circuit. These are found in 230.31. Conductors, ampacity correction factors. Both of these you're going to find on the exam. Ampacity. The ampacity of a wire is affected by heat and the following: insulation type, conductor material, number of conductors in a raceway, conductor size, surrounding air temp. Heat adds resistance. I'd write that down. Heat adds resistance. So it is up to us to install in a manner that dissipates that heat without breaking down the wiring. In order to do that, we're going to use different tables to determine the ampacity of our conductors. Again, things to consider: ambient temperature. Are we installing it in an area that's hotter or colder than table 310.16's temperature rating? Number of conductors. Is there more than 3 current carrying conductors in the raceway? What's the termination rating? Are we terminating this on a 75 degree lug? Are we terminating it on a 60 degree lug? What's the termination rating? And then location. What's our altitude? Are we in the Rockies? Here in Indiana, it's not a big deal, but in the Rockies, altitude matters. Ambient temperature and conductor heat contribute to insulation degradation. That's why we need to pay attention to what our installation requires. Now, the tables you need to use for determining ampacity are these tables here. 310.16. 310.16 is for conductor ampacity. 310.15b1, temperature changes. If we're installed in a lesser or greater than temperature than the rating found in 310.16. And then 310.15c1, number of current carrying conductors in a raceway. The ampacities found in table 310.16 is based on no more than 3 current carrying conductors in a raceway. If there are more than 3 current carrying conductors in a raceway, you're using table 310.15 to make corrections. 310.15c1. So for example, we have a load here, and the wire to load number 3 is 6 gauge, the wire to load number 2 is 1 gauge, the wire to load number 1 is 2/0. Each of the loads is 3-phase, 3-wire, in the conduit with 9 conductors. How much current can the wire to load number 3 carry in the high temperature area? High temperature area right here is where I'm worried about for this conduit, for this question, because we're only looking in the conduit with 9 conductors. How much current can wire to load number 3 carry in the high temperature where the temperature is 133 degrees Fahrenheit? So I'm looking at these 9 conductors, load number 3, high temperature area. It's a 6 gauge wire, and I'm considering only this area here. I then go to table 310.16 to look up the ampacity of my number 6 wire. And my number 6 wire, I believe in the question, wanted it to be THHN, which is a 90-degree wire. So I'm going to look up 90-degree wire for any correction factors for THHN. So number 6 wire in THHN is 75 amps. 75 amps for my number 6 wire. Now that I determine my ampacity, I go to table 310.15b1 to determine my temperature correction. And we said it was 133 degrees Fahrenheit. So this guy right here means I have a temperature correction of 0.71. And I'm using the 90-degree column because I'm still using THHN. It's a 90-degree wire. So all my correction factors need to be based off that 90-degree column's percentages and factors. So I start with 75 amps with a correction factor of 0.71. Then I go to table 310.15c1 for my number of current carrying conductors, which we determined was 9, meaning I have a correction factor of 70%. 70% for 9 current carrying conductors. Now let's do all the math together. I start with 6 gauge wire, which is 75 degrees in the 90-degree column, 71% for my table for temperature correction, and 70% for 9 current carrying conductors in a raceway. I multiply all that together. 75 amps times 71% times 70% gives me a total of 37.275 amps. That 0.275 is negligible. My answer for this question would be D, 37. 37 amps is what that 6 gauge wire is capable of carrying through that high degree area. Under normal circumstances, 6 gauge could carry a lot more than just 37 amps. But because it's ran in a conduit with other conductors, and it's in an area that's hotter than it's rated, that 6 gauge wire is only good up to 37 amps. Now, there's some other items on your exam that you'll run into. And I want to give you these code references to look up and study from, because you'll see random questions throughout the exam based off these code areas. Hazardous locations, Articles 500 through 503. Remember your different types of hazardous locations. What's a Class 1, Class 2, Class 3? Healthcare facilities found in Article 517. Clearances found in Article 110. Remember to use Table 110.26 when determining clearances away from ungrounded wall and equipment, between equipment and a grounded wall, and between equipment from other live equipment. Overcurrent protection devices. Standard sizes are found in 240.6, Table 240.6a. Equipment and appliances found in Article 422. Flexible cords found in Article 400.5. Voltage drop. Now you will have a couple voltage drop questions, so go back and look at your notes for voltage drop equations. Remember the voltage drop equations found for three-phase versus single-phase. And all of the different variations of the formula. Remember, for single-phase, volts dropped equals 2K. Hold on, that's a bad K. 2 times K times amperage times length divided by circular mils. And that's for single phase. For three-phase, volts dropped equals 1.732 times K times amperage times length divided by CMA. And then generators found in Article 445. Be sure to review your notes over these subjects and recall the code references for each. You will see a couple voltage drop questions on the exam. Yeah, I hope that this has done its best. I hope that this video has been helpful for you in preparing for the final exam. Again, review your notes, do your best. I've provided a study guide to go along with this video for you to fill out notes as we go. Please take the time to do that. It'll be helpful for you. There's also a quiz this week. It's a take-home quiz. It's a review quiz found in lesson 235. That will be a quiz grade. So if you do not do the quiz, you will get a 0 on that quiz grade. And I highly encourage you to do the quiz, as that's a big part of your grades. If there's any questions about the exam, feel free to email me at ed.brown@iec-indy.org. And I'd be happy to answer you as best as I can. Again, for the exam, code book only, calculator, handwritten notes. I will allow the handouts like the box fill handout, the RLC handout, the Transformers handout, anything like that, you're welcome to have out. But when it comes to the test, no workbooks, no old quizzes, no old homework, no manuals, just your code book, just your calculator, and just your handwritten notes and handouts. So please go back through this video, use the study guide, use that, take notes, take handwritten notes on your study guide. Yeah. So again, if there's any questions, please reach out. Best of luck. I'll see you guys at the lab tonight's class. Talk to you later.